In the second tutorial, you're going to find out what an empirical formula is, and you're going to learn how to calculate them. So what? Why do you care? Well, it is because using these methods, scientists figure out what the actual chemical formulas are of new substances. For instance, they might discover a substance in a plant from the Amazonian forest, and it brings down fevers, and they want to know what it is so they can make it and market it. So they test it, they break it down, they figure out what the formula is, and then they can make it in the laboratory. And this is part of what makes science fun, figuring out the new stuff. So we're going to deal with these things called empirical formulas. That word empirical means it is based on experiments. It is not somebody sitting around and saying, well, according to the theory, we ought to have this many atoms of this bonding to this many. They actually do an experiment and determine weights, masses, and figure out what the compound really is. Scientists collect the data in experiments and use it to determine empirical formulas. Here's the definition. The empirical formula of a compound is the simplest whole number ratio of the atoms present in the compound. We can get it from percent composition data, or we can get it from masses. Here are the steps to the method. However, we're not going to get into them in a lot of detail right now. You can also refer to your handout tomorrow in class to remind yourself of these steps. Before we read those and learn how to do them, we're going to talk about moles again. To do this technique, you really need to be able to figure out how many moles you have in a certain mass of a substance. The way you do that is you divide the given mass by the molar mass, which you figure out from the periodic table. We learned how to do that in the last tutorial. So, how many moles are there in 36.03 grams of carbon? Divide by the molar mass, 12.01 grams per mole. Cancel the units, you end up with moles, 3.00 moles of carbon. Note, I use detailed labels, moles of carbon. This gets to be important later as problems get more complicated, so you might as well get into the habit now. Also, note, this problem, according to significant digit rules, should actually be reported to 3.000 moles of carbon. So let's do another one. How many moles are in 6.06 grams of ammonium sulfate? Well, we have to figure out the molar mass of ammonium sulfate. I'll just let you read what's going on there. We did this in the last section. The mass of the nitrogens, the mass of the hydrogens, remembering that the subscript 2 means there are 2 ammonium ions, the mass of 1 sulfur, the mass of 4 oxygens. Add them all together, and you have the molar mass of ammonium sulfate. So to figure out the mass, or the number of moles in 6.06 grams of it, you set up a factor label problem. Grams of ammonium sulfate divided by the molar mass gives you moles. 0.0499 moles of ammonium sulfate. I'll report it to 3 significant digits because that's the value we started with. So let's look at how we calculate the empirical formula from masses. Obtain the mass of each element, determine the number of moles of each type of atom present, divide the number of moles of each element by the smallest to get a whole number ratio. Let's do one. If we have 13.5 grams of calcium and 10.8 grams of oxygen and 0.675 grams of hydrogen, what is the empirical formula? First, we figure out how many moles of calcium. Divide by the molar mass of calcium. Then we figure out how many moles of oxygen. Divide by the molar mass of oxygen. Then we figure out how many moles of hydrogen. Divide by the molar mass of hydrogen. And we get these values. Now, those aren't whole numbers. We need whole numbers to use as subscripts. We're guaranteed at least one whole number if we divide all of them by the smallest. 0.337 divided into 0.337 equals 1 mole of calcium. Divided into the moles of oxygen, you get 2 moles of oxygen. Divided into moles of hydrogen, you get 1.98, and that is very, very close to 2 moles of hydrogen. You can round it to 2. So our ratio is 1 to 2 to 2. Does that look right as a formula? Not really. Remember, polyatomic ions. And you can actually check that using the crisscross method to see if that makes sense. Now, we can also do this from percent composition. It's the same procedure exactly with just one little twist. We use percentage. We're given percentage. So it doesn't really matter. If you are given grams, we calculate the molar mass using grams. If you're given percent composition, you change the units from percent to grams and calculate the moles by dividing by the molar mass. You can assume a sample size of 100 grams to do this. Why do we do it two ways? Because sometimes in experiments we record mass, and sometimes we use an instrument which reports back percentages. So here's an example of percentage. If we have 80% carbon and 20% hydrogen, we assume a 100 gram sample. That means we would have 80 grams of carbon in the 100 gram sample and 20 grams of hydrogen in the 100 gram sample. Figure out the moles of carbon, figure out the moles of hydrogen. Divide by the smallest. And you end up with a ratio of carbon to hydrogen 1 to 3, CH3. Notice that the 2.97 is awfully close to 3. You can round that number to 3. You need whole numbers here. Now, here's the last trick you have to learn for doing that. And that's what to do when your mole ratios don't come out very close to a whole number. You start out the same. You get the mass of each element or percentage. You determine the number of moles present. You divide all the number of moles by the smallest. But if one or more of these are not whole numbers, you go on to step 4. Multiply the numbers from step 3 by the smallest whole number that will convert all of them to whole numbers. That's not going to make sense till you do it. So let's do it. Some of the things you'll have to look for in order to do this are as follows. Sometimes when you divide all the mole values by the smallest, you do not get whole numbers. You get some decimal equivalent of a fraction. In that case, you have to recognize the fraction and multiply by the denominator to get rid of the denominator. So for instance, if you get 0.5, you can recognize that as 1/2, the decimal equivalent of 1/2. You multiply all your values by 2 to get rid of the denominator. If you get 0.25 or 0.75, you recognize those as fractions which have 4 in the denominator, so you multiply by 4. 0.33 or 0.67 are thirds, multiply by 3 to get rid of it. This one's kind of weird, you don't see this one much, but 0.17 is the decimal equivalent of 1/6. You would multiply by 6. Multiply all values by the denominator to get the whole numbers. Here's just kind of a picture form of what we just talked through, if it helps you. If you have a 0.5, multiply by 2. 0.33 or 0.67, multiply by 3. 0.25 or 0.75, multiply by 4. 0.2, multiply by 5. 0.17, multiply by 6. This still might not make much sense to you until we do one. So let's do one. We have 10.150 grams of a sample. 4.433 grams are phosphorus. The rest is oxygen. How do we figure out how much is oxygen? Subtract. So there are the numbers you need to start with. Figure out the moles of phosphorus. You divide by the molar mass to do that. Figure out the moles of oxygen. Divide by the smallest. Now you got 1 for your phosphorus, that's good. But when you divide the oxygen by the smallest, you get 2.497. Now that is not close to a whole number, but it is close to 2.5. So you have 1 mole of phosphorus, and you have about 2.5 moles of oxygen. 2.5 can be expressed 2 and 1/2, or 5 halves. You need to get rid of that 2 in the denominator. To do that, you're going to multiply by 2. If you multiply one value by 2, you have to multiply the other one by 2. So you end up having 2 phosphorus for every 5 oxygen. There's your ratio. Here's how you write it. And that's the end of this tutorial. Come to class ready to work on these problems tomorrow. Thank you.